section 5.5, alternating series. So now what we're talking about today is alternating series. We dealt with series so far, and most of them are positive. So here we're going to actually get into the series where we're actually dealing with these alternating signs. So here, how we get a plus, a minus, plus, minus. And what we're going to do with these is we're going to run these alternating series tests on these for the most part. Okay, so here down below here, this is how it's defined. So what we're going to do is we're just going to take a few of these and just kind of play around with them and get used to writing them and whatnot. So this is what we're going to end up doing. Okay, so take a look. We have this theorem, alternating series test. And this is actually we're going to spend a lot of our time on in this section. Half of our time, I should say. Okay, so the first thing to realize here is notice an alternating series of the form blah. So it has to look like this in some sort. And then they say converges if this condition is true and also this condition is true. So what we're going to do is we're going to take a series that looks somewhat familiar to us. And that series I want to take is this one here. And you may or may not remember this, but if I take this piece away right here, that's just the harmonic series. They call this one the alternating harmonic series. So what we're going to do is we're just going to actually use this alternating series test on this thing, hopefully, assuming that we can get these two conditions to be true. All right, so first things first. So if the alternating series test is going to work here, I have to first show, and what this simply means here is that it's decreasing because it's saying the n plus 1 term is less than the n term. So it's a decreasing function. So again, how do we find decreasing functions? By simply taking the derivative of that function. And that's another thing to keep in mind too, that the b sub n is only the piece multiplied by the 1 over n, or multiplied by the negative 1 to the n, excuse me. So when I actually take this derivative now, the 1 over n, it's going to be negative 1 over n squared. And hopefully everybody's okay with that. If you're not, let me know, and we'll talk more about this. So anyways, so going from here, I can see that for every n bigger than 1, that it's going to be less than 0. So therefore, I can say this implies condition 1 is true. Now, the next part says, when I look at that second piece now, this one here, I have to just take the limit of it, and it has to equal 0. So therefore, that simply means, okay, now let me take the limit. So I take the limit of 1 over n as n goes to infinity. Now for this problem, it just seems like a lot of hand waving, and it is kind of, because that equals 0. Now because condition 1 is true, and the limit of 1 over n as n goes to infinity is 0, then I can say this implies by the alternating series test that the series from n equals 1 to infinity of negative 1 to the n times 1 over n converges. Done. There's that problem there. So now what we're going to do is we're going to try one more. Now on the next slide, I have this problem already set up for us. Okay, so you might want to take a second to write it down. So the first thing we have to show that this is a decreasing function only for the b sub n, which is this piece here. Okay, so all I'm going to do is take the derivative of that. Now this one, it's going to be a little bit more difficult to take the derivative. Because what does that mean? The derivative of the top times the bottom, so it's going to be 1 times n cubed plus 1, so it's going to be n cubed plus 1, minus the derivative of the bottom, excuse me, which is 3n squared times the top times n, all over the bottom squared. Now this is the best way to do these using that quotient rule. It makes it the easiest, and you can see what 0 is, or I should say what positive and negative are right away. and also what the zeros are. So anyways, so this simplifies to negative n cubed over n cubed plus 1. Oops, I forgot my little squared here. Squared. Okay, so that's what it simplifies to. So I can say that this is definitely going to be less than 0 for n greater than 1. Oh, n greater than 1. And if we take a look at that condition there, that's kind of what that said for us, didn't it? For n greater than or equal to 1. Okay, so knowing that, I should say, equal sign 2. That's good. Okay, so now what we're going to do is we're going to actually look for the second condition now. So this is that condition 1 that we actually met here. So now condition 2 says what? I'm going back. That the limit of that sequence has to be 0. So now all I'm going to do is take the limit of it. Limit as n goes to infinity of n over n cubed plus 1. Now there's different things that we could actually do for these to kind of figure out what's going on. I can actually divide that. I could say, okay, let me divide all of my top and bottom by n. I can do that. And that's the path I'm going to choose here. Now, this is something you probably learned in Calc 1, hopefully. And if you didn't, here it is. And this is all the detail, too, so you can look at this and say, okay, this is enough to know what I need to do. So then this down here is going to be an n squared now because I got to distribute my negative. I mean, not my negative, but my n when I divide for both of those. So that's going to be n squared plus 1 over n. Now this is actually my limit here. So what I can say is this piece right here goes to 0. Okay. And that means I'm going to get that 1 over infinity that you guys write, but please don't write that. You can simply say this, that goes to 0. So then the 1 over infinity, that equals 0. And for me, I think that would be enough to say that. That is 0. Okay, so there's that second condition now. And now, since both those conditions hold here, then I can say, and I could say this, and maybe here. Condition 1 is this, and 2 implies the series n equals 1 to infinity of negative 1 to the n plus 1 times n over n cubed plus 1 converges by the alternating series test. And you can write AST, I'm fine with that. So there's our second problem now. So that's kind of how this alternating series test works.